Welcome to the course on FPGA based signal processing systems. This week lectures are based on the synthesis of combinational and sequential logic circuits. Basically, this lecture focuses on the synthesis of combinational logic circuits. If you recall that the synthesis process and the design flow, the very first hierarchical block diagram, using pen and paper, we draw what is the digital circuit is, then you do the coding Verilog module, and then compilation, and then we have verified with the simulation, which is the functional verification only, doesn't involve any timing verification in this. And then if there is any mistake, or if there is anything the functionally incorrect, then that would point to the previous steps as shown over here. And then we come to the synthesis part, that after learning the designs in the combinational and sequential logics and the and the simulation of them, we come to the synthesis part to target this code in the FPGAs. So the synthesis contains the find the Verilog equivalent, what the digital circuit and the module has been saying, to the hardware counterpart. Actually, if there is any hardware counterpart which you want to deploy in the FPGA exists or not, so your code is synthesizable or not. So those things needs to be considered, otherwise the whole design needs to be done again, or the Verilog module should be modified. So the synthesizable code needs to be written, or the model to be developed. So in this case, after synthesis, that you have this fitting and place and route, depends on the targeted FPGA, and the timing verification is also done. While doing the timing verification, the functionality can also be little bit added and checked, but usually functional verification and timing verifications are mutually exclusive. If there is anything wrong at that stage, yes, we have to go and correct it to the first stage. Otherwise, this is here to the fitting and the place and route is possible. So now we will be focusing on the synthesis of the combinational logic circuits. What are those are definitely synthesizable? What would be the problems? What should be avoided in the Verilog code, so that how it gets synthesized, or that can be discussed now. So the coming to the synthesis tool, so usually the synthesizer helps in the synthesis tools, helps in making the synthesis process anyway. So what are the functions of the synthesis tools? So one is that it detects from your digital circuit, or the module Verilog description. From that, it is detecting and eliminating redundant logic. If there is any logic which is redundant or needs to be omitted, and it finds out any feedback loops in the combinational thing. So it detects the combinational feedback loops, which feedback loops allowed in the case of the sequential thing, whereas in case of combinational logics, if there is any feedback loops, that needs to be dealt differently, or exploit the don't care conditions. So how the don't care conditions should be used in the hardware in the synthesis process, whatever, if it is saying X or Z in the high impedance state, X is 1 or 0, so should be definitely said to the hardware that what is the how to use this don't care condition, and detect the unused states. If something is not used at all in the code, detecting them, and detect and collapse equivalent states. So some states may be equivalent, so detect those things. Also the mix some state assignments to reduce the number of states, so that would also be possible. The optimum states can be found. Synthesize optimal multi-level realization of logic. So the logic which is given, some of them may have the multi-level logic, so but that needs to be optimized in the case by considering the constraints of area and speed. So area minimization and speed should be high. So this optimization needs to be taken care while doing this the synthesis of multi-level logic realizations. So especially finding redundant feedback loops, how to handle this don't care condition, is there any unused state, or is there any state minimization required. So those things has been dealt by the synthesis tool. And then synthesis can also be done. I mean, three types of synthesis we can have. That one is logic synthesis. I mean, this or another one is this RTL synthesis, whereas the third one is the high level synthesis. So the part which is here, the logic synthesis, is the code, Verilog code which is written, the module is converted into internal representation. So whereas it can be of Boolean equations, or that is equivalent to combinational logic or storage elements. So the conversion from this code, Verilog code, to this representation is this logic. What is the logic behind that? Combinational or storage elements are used sequential. So those contents been the outcome of this HDL description in the logical synthesis. Whereas in the case of RTL synthesis, where we have this code, HDL description to a technology specific logic circuits, like gate level netlist will be generated in the RTL. RTL we mean here is that register transfer level. So register transfer level synthesis finds out the which technology will be used and what is the specific logic circuit for that technology. And based on that, the gate level netlist will be generated. High level synthesis is very it is used for algorithms. Suppose we did especially this DSP algorithms, we want to deploy into the FPGAs, then it is essential to have the complete architectural. This is based on the architectural or the behavioral synthesis, high level synthesis. So in that case, the data path elements, control path and the memory are to be decided, how this algorithm goes through this data path and control path. Also the memory required for this algorithm to be executed in the FPGAs, and it is also very much concerned about the resource allocation and the resource scheduling. What are the resources should be used and how the resources are going to be scheduled according to the time, and then that will be dealt in the high level synthesis. So just to distinguish these three here listed, and we will be looking at the things, these of them, these everything, and in the coming explanations. So when you take the synthesis tool, anyway, this is a Vivado environment, you will have you'll have this listed over here after writing the Verilog module, and then you can get into the flow navigator where you have the run the simulation. So you will have the waveform editor and using the test bench and so on. After doing this process, you can get the RTL analysis where in which it gives you the schematic at the end with this is called the RTL schematic. What is the equivalent logic, the gate level netlist for the code for the Verilog module. Similarly, if you run synthesis, then that would give the schematic, and it will also go through a set of processes here, and the schematic which is giving the technology schematic. So the technology schematic will use mostly the LUTs. If you recall the very first few classes of that, we use this LUT, and then the logic blocks, and then multipliers which are used in this case, and switches and the interconnects and so on. So the based on the technology, this would give us the view that which your Verilog module uses LUT or the registers or the latch or mux, what are the mux, the multiplexers it is using. So those details will be given, that will be this portion will be changed to the technology specific view. So that we would see. After that, along with it, you will be getting some reports of this timing analysis and utilization report and summary of the code, the resource summary, what are the resources have been used from the FPGA, and then we can get into the implementation, just generating a bit stream for the code and then dumping into the FPGA. So this process we are now doing the synthesis one. The synthesis converts this Verilog RTL code to the gate level netlist in the RTL. It also performs, as I said in the first one, logic optimization, resource mapping, is it checking for the resources, timing analysis, and it is ready for the implementation of the and get the output for it. Also, it when what are the points to be remember when we create a project in the tools, synthesizer tool, that is the create a new project. When you create a new project, you add the Verilog source files, that is design file, and the test bench for simulation. Also it needs select the target FPGA, that is the which FPGA we will be using. So if device name needs to be chosen in the synthesis process, so that it identifies that device and what are the resources available in that FPGA, and you try to use that resources in the synthesis process. So and the constraint files are added instead of in the real time. If you have in the simulation, you use the test bench to give the stimulus, whereas when you want to dump the code in the FPGA and it want to run your algorithm or a digital circuit in the FPGA, then the inputs and outputs are not from the test benches, it is the real time inputs. So the FPGA boards will have this type of switches giving the input, or through the A to D converter you can communicate to the FPGA to give the input signal. So what are the pins are communicating to the input and outputs, so that details will be given in the constraint file. The constraint file also carries the information of the which pin is dedicated to the clock, okay, apart from input IOs. So these are to be added in the synthesis process. That is only synthesis just to see the schematic view, it may not be required to have the constraint, but if you want to see the outputs and dumping the code, and then constraint is mandatory. So as shown here, this is essential while creating the project to have this Z board for the example. The name, the chip name needs to be, or the board which you are going to use and the chip name are important to be selected before the synthesis. And then run the synthesis, anyway the one which is shown over here, it performs this parsing and elaboration of that, also the logical transformation what is required, technology mapping, and then report generation. So this, after doing this mapping and translating your code into the FPGA resources, understandable ones, and then get the report generation, which has the all the utilization report, how many resources have been used, and what is the timing report, what are the critical paths in that, that details would be given in the timing report, and the schematic viewer of the what is the technology schematic, that is also generated as the output of the synthesis process. So after this is just a list a few things that when you do it in real time, yes, you will be having the hands-on experience on that. So this the combination logic, when we consider the combination logic synthesis, what are the points to be noted, how to write the synthesizable code of the combination logic. So we have done this combination logic circuits that, and that it is if you recall that there is a structural model, a structural data flow and the behavioral models, especially in the structural primitives. When we say instantiation of the built-in gates, if you recall, those are the netlist of, if you have this list of structural primitives in your Verilog code, those are synthesizable to combinational logic. And the set of continuous statements, if you have these continuous statements, either one or multiple continuous statements, so the continuous assignments also synthesized into combinational logic. And level sensitive cyclic behavior, here we means cyclic means always at the rate A or B. Okay, so the A or B, not the passage of the clock or neggage of the clock, the level sensitive, A is 1 or 0, B is 1 or 0. So those kind of structures, the code Verilog modules are synthesized into combinational logic. So combinational logic, when we consider it, is not only the structural one, so the level sensitive behavior of always block within the sensitivity list, if you have all the inputs A, B, or for example, also synthesized into combinational logic, and continuous assignments as well. Let us see the one example of a structural, and then another some for assigned statements, also the level sensitive behavior. So one is that module, here is the module name. So we have input A, B, C, D, E, 5 inputs and 2 outputs. This can be that one AND gate instantiated and y1 a comma c, y2 a comma d, and then y3 a comma e. So for example, and then comes the OR gate y4, which is taking y1 and y2 are inputs. So if you remember, these are inputs and y1, y2, y3 are out, y4 are outputs. Similarly, y out 1 is output, y3 and y4 are inputs to the OR gate. So other set of the instantiations, and BC, BD, and then B are inputs, y5, y6, y7 are outputs to it. So that OR gate, similarly y7, y8 are input to this OR gate, and y out 2 is the output. Similarly, y5, y6 are inputs to this OR gate and y8 is the output. So this set of instantiations are synthesizable. The primitives, structural primitives are synthesizable into, these are into combinational logic. So if you see the RTL register transfer level schematic of the code, just run this RTL analysis in the environment, in the simulator environment. A and E, which is from this code, you can see A and E, which is for y3. Okay, so this is y3, and y1 takes the input from A, and so this is from C. So the code is just translated into RTL register transfer level. So this uses 1, 2, 3, 4, 5, 6 AND gates as prescribed in the code. 1, 2, 3, 4. There are 4 OR gates. Okay, so each in one set of instantiation. One set for this, and another one is, so this is actually a mimic of the circuit, which is same as that two AND gates, and so on. So this is one, another one, 3. So we have the set similarly here. This is 3 and 2 OR, 3 and 2 OR. So that's what is given over in the y out 2 and y out 2. This is a schematic which you get from the when we say RTL design. This is the design of this code. Okay. So and then if a technology specific one, so to FPGAs and the board which we had chosen, so the equivalent code, equivalent logic, combinational logic is now taking the input A, E, B, C, D, E. Okay, so all of the inputs, 5 inputs, and uses the buffers. Okay, so these are the buffers given to the, this is technology specific, uses some buffer, and then you can see the LUTs. For y out 1 there is one LUT, another y out 2 there is another LUT, which uses 4 input LUTs. So this is picked up according to the FPGAs which we use. So here is for the Z board one, we had the I0, I1, I2, I3, and 4 input LUT is used, and each output has the buffer as well, y out 1 and y out 2. So this is the technology schematic of the code which is written over there. So if you check the each LUT, what are all the things it is doing? It is doing optimization and the Boolean equations. The input output behavior of your circuit is now understood by the simulator in the synthesizer. I0, I1, I2, I3. There are 4 inputs, and what is the logic to be followed here? Okay, it is getting the Boolean equation for it and list the output. Okay, based on this output, it also so the again y out 2 similarly get the output. The inputs are I0, I1, and the lookup table inputs, which are basically from the input to the gates in that. So the gates, the primitives instantiated are now converted into, in the technology schematic, converted into lookup table information with the Boolean expressions here, and this Boolean expression is even minimized using a Karnaugh map that is minimized, and then this is implemented. So output you will get it here. This is, if you just click on the cell properties of the LUTs, and you would get this detail of the truth table which is used in the LUTs. So the LUTs 4 inputs, what is the output for it? So what is the logic behind this? If you get this inputs, what is the output, and the logic behind is also synthesized here. And this is for the previous example. If you come to the next one here, that continuous assign statements, that is for the primitive gates, structural primitives. Yeah, it is synthesizable. When the continuous assign statements, yes, this is for example module X input enable x1, x2, x3, x4. This is another example which has 5 inputs and 1 output, including enable as an input, and assign y tilde enable and x1 or x2 and x3 or x4. So, this one is how this is getting into a synthesis process, how it is getting synthesized. So, assign statement is synthesizable, that is continuous assignments are synthesizable. So, here, so that is, this is especially synthesized into a combinational logic. So, the RTL schematic, the code which is here. So, RTL schematic, if you run the RTL analysis and then you get the design, RTL design over here, the enable and x1 and x2 are given to the OR gate, this portion, x3, x4, this OR gate, this 2, and then this outputs, this one, and enable here, you can see then and then this and this is this is a function of this and you get the tilde here, that is invert. So, this is a schematic which is the equivalent the code is made of, and then the technology schematic which is using the LUTs. You can see the LUT size keep increasing, that is a 5 input LUT now. In the previous case it was 4 input LUTs and it is 5 input LUT. All the inputs 1, 2, 3, 4 and enable are taken, and the output, which is everything is included in the LUT function. Boolean expression is found and then it is minimized as well, the output will be. So, this is only using one LUT with some buffers and the buffer at the output. So, 5 input LUT is used for that logic, and the truth table of the LUT, if we take this and the equation which is equivalent to the assign statement is over here. So, which is listing the outputs as well. So, this is going to be the truth table which is shown for the technology schematic. So, even the Carnap map and other things also is done for the minimization using these outputs. And then the third category, which is synthesized into combinational logic, is a level sensitive cyclic behavior, always at the rate of what is in the sensitive list, which is level sensitive, not edge sensitive like in the flip flops. So, the synthesizable Verilog module, which is of combinational logic, it describes the functionality of the code, yes, and then it is written independent of the technology, the codes what we are writing. It can be dumped into any of the FPGAs so in that case the circuit which is to be realized is only common, whereas the technology is not common here. And so, when we give the timing constraints, that is only time when you do the timing analysis, that speed of the circuit is tested using this timing analysis. Functionality is not tested. If you recall the HDL design flow also, the timing analysis and the functional verifications are exclusive. Using the when you do the timing, 1 or 2 input cases can be given and tested for the functionality after the timing analysis. And in the case of timing constraints, it is purely the timing one, and the delays related to the gates and other things should not be included, the technology dependent timing. Okay. So, for this for that particular technology, the delays for the gates would be different, so that need not be included in the code for the synthesis. So, what is that level sensitive behavior? It is of feedback free. So, if we have the NAND gates and the 2 NAND gates should not have any feedback. So, that is, one output should not be connecting to the input, another output should not be connecting to the input. Cross coupled structure should not be there in the synthesis process for the combinational logic synthesis. One. And the functions and tasks may be synthesized into combinational logic, but if there is anything like case statement, if statements doesn't have the default case or all the options for the outputs. Similarly, conditional statements, if statement did not have else statement, so that would be it won't have the combinational, it won't synthesize into it actually. So the combinational logic will not be getting from that, it would form a latch. So pure combinational circuit will not be possible with the conditions which doesn't have mutually exclusive conditions. Also the case statements, some of the default cases or the outputs are missing, so then it would infer a latch. So then it is a care should be taken for the feedback free loop, and all if conditions should have the else conditions, case should have the default case, or it should have all the combinations of case items. And if there is, if it do not contain any timing controls, hash, at the rate or wait, all of them also should be taken care. So it will be synthesized for implementation of the case construct and the conditional operator as well. So combination logic should have this details, so that this can be synthesized into combination logic. Otherwise, the case construct and the conditional operator should be taken care for the combination logic synthesis. If you have your code as that one, it should not contain any timing controls as well, hash, at the rate, and then or wait. So in the continuous assignment statements, again, once again, if you see what is the module the third example here, input select some signal G and signal max, signal A and signal B, 1, 2, 4, 5 inputs, and then output Y. So assign statement, Y is equal to that select equal to 1, or select G equal to 1, this one, or sigma max equal to 0. If this logic is true, you see a logical expression, then assign Y equal to signal A, otherwise signal B is assigned to it. So it has a logic. So how this will be synthesized into? So this is a ternary operator, conditional operator, saying if this condition is true, assign it, assign signal A, else Y should have signal B. Yeah, mutually exclusive conditions are all conditions are specified. Okay, so in that case it has a logic. So how, let's see that how it is getting synthesized in RTL schematic. If we can see the signal A, signal B, select signal G and signal max. So select a signal G, this OR logic, and then OR with RTL signal max here. If it is equivalent to 0, you can see how this is taking the equivalent in RTL, and then this is given to a mux. The usually mux would have a select line of 0 or 1 if it is a 1 bit, or if it is 2 bits, then it will have 0 0 0 1 1 0. So 2 bits. So here it's instead of having a select line, so this mux has the control logic as select line. Okay, so this control logic which is used in the condition is coming as a select line control logic, whereas the input signal A and signal B, that is what is to be assigned. The signal A or signal B, if the condition is true, I0 will be assigned to Y, if otherwise I1 will be assigned to Y. So this is signal B. It is forming a mux structure, yes, but the select line is decided by the control logic what is given over here. If we see that it is synthesized into a mux instead of a select bus. So the technology schematic, it takes again the, if you see that it is LUT has this 5 input LUT, and taking the whole logic what we had seen, the mux structure with the control logic is synthesized with the Boolean equation here, showing the outputs what is required for these cases, that is having the 5 inputs here. So all the cases have been considered in this synthesis process. So this is from the technology schematic. So coming to the priority structure, so where the priority structures are getting synthesized. So in the case of case statement, okay, so if you take the case statement, it is implicitly saying the higher priority to the first item case. Suppose yes reg case A and we write the condition if enable is true and what is the case. So, the first item gets a higher priority implicitly, and if we should, that is why it is should give all the output all the case items should be listed in the case statement. Case and in the if, suppose if we take the if statement, the higher priority to the first branch, okay, compared to the remaining branches of the if statement. If, what is the condition? Else if, else if, what is the condition? Else if structure if we have, then which has the highest priority to the first branch. The synthesis tool, what it will do is it will check the mutually exclusive case choices, and if it is there, then the mutually exclusive cases are there, that is case items, everything is listed, then it treats them, all of them, with equal priority. Okay, so in the cases, in case structure here, so instead of having the priority structure, so a mux structure is synthesized instead of a priority structure. So, when the mux structure, when would be the priority structure gets synthesized, the code will be synthesized into mux or priority structure if you have the mutually exclusive cases or exclusive condition in the conditional operator, then mux structure would be synthesized rather than a priority structure. So, we would see that an if statement will be synthesized into mux structure when branching is specified mutually exclusive conditions, otherwise priority structure will be doing that. So, in the case of suppose we have this event control expression, always at the rate is this in the cyclic behavior, it monitors all the signals, that is if there is any change in the sensitivity list of the signal, whatever is assigned it should be within the behavior you will be using ABCD, that will be executed. So, event control expression should have in the sensitivity list, should have all the inputs. That is what we emphasize, that all cases of input should be available in the sensitivity list. If not, then it may, there is a chance of inferring a latch in that process. So, the conditions are not mutually exclusive, then priority structure, again say that mux or priority structure, which one would be taken into. So, by the synthesis tool. So, if statements, again we will take an example here, example for input A, B, C, D, select A, B, select C. So, output average. So, always at the rate select A, B or select C or A, B or C, any of this, you see the list of, always the sensitivity list contains all, or you can use asterisk simply instead of this to simplify the code. Begin if select A is 1, yeah, first one is 1, Y is A, automatically we give the priority to select A irrespective of select B, select C or anything. So, in else if next is select B, okay, Y is equal to B, else if select C, the next one, what is the condition? Y should be C, else in all other condition if these things are there, then Y equal to D, end. So, in this is purely the case of priority structure. We can see the RTL schematic in which priority structure should be synthesized, whereas it has a mux structure which is due to the if condition, this one, else again this. So, for this if there is else, so because of that it is giving. So, you can see for A, for example A it has, but else condition is coming from the other one, else C is checked, C and D which are given lowest priority here. Okay. So, automatically there is a priority structure, yes, this A is given priority over here, this input of this of the mux which is decided from the output, and then from CD has the lowest priority, and then the B, the A is the first priority. Okay. So, here you can observe the priority structure which is given to A rather than B and CD. Okay. So, this is a schematic, and this technology schematic again is given here. So, you can see the A as the highest priority with the LUT, which is this is the priority structure again with LUTs A, and we have this select A, okay, and the output of this CD and B. Yeah, what is the condition on that? Which has the LUT, 5 input LUT and 3 input LUTs are used. Anyway, this is again this has the mux structure which is used in the RTL along with the priority structure. So, is synthesized using the technology schematic as like this. We also get the truth table for the logic which is synthesized over here, and the second LUT has this logic I0, I1 and I2. So with this we have seen a few cases of the combination logic synthesis, that is the structural primitives and then assigned statements, and case and if statements should have the default cases, or all the case statement should have the if default cases, and if statement should have the else condition. So otherwise it would infer a latch, whether the priority structure or a Mach structure depends on if you explicitly specify all the conditions, yes, it will go for the realization of Machs. If not, it will be a priority structure. So we'll continue with the synthesis of the combinations, a few more example and sequential logic in the coming lecture. Thank you.